Why do we get that flu shot every year? What? You don't get that? We need to have a talk. Our immune system can be sensitized to recognize infectious agents. We call these things antigen. And this can happen before they enter our body. It's all based on the actions of APCs. Remember that? Macrophages, dendritic cells, T cells, and B cells all are involved in this process that keeps us from being infected. Passive immunity may seem like a lazy way to go because a patient is given antibodies from another source. They're sort of loaned to give temporary immunity because the person is not making enough of their own antibodies. They're fighting some infection, they're weakened, they need help. We get passive immunity before we're born, when white blood cells and IgG antibodies flow across the placenta. Soon after being born, the first few days, we get an antibody-rich fluid called colostrum that's in breast milk. And that's why mothers often don't leave the hospital until their baby has latched. There are experts that from the Lecce Society and other organizations that make sure that this happens. Acquired passive is what I've been talking about. It's a way to give patients time for their own body to develop the antibodies they need. But we also use it in things like gamma globulin for travelers or healthcare workers that are soon to be exposed to something perhaps new or deadly. And maybe they're traveling to Africa in areas with extreme disease problems. A second major form of immunity is called active. And let's just take a look at this diagram I have. The antigen at the top with its surface marker. All living things have self-surface markers. And that helps us to tell self from non-self. We're going to strip off that MHC surface marker, put it in a hypodermic needle, inject it, and that is going to trigger the body to make its own T and B cells. This is an old method, this antigen exposure, but it still is used for some pathogens that just don't seem to respond to more modern vaccines, such as genetic recombination. I'll be talking about that one. There is some danger with this antigen exposure because if you see my circle, there is live virus in this case. And how do you feel about that, being injected with a live virus, HIV or something like that? And this is the basis for a lot of fear. Unfortunately, these old vaccines, such as some of the early polio vaccines, used antigen exposure, and people got polio. So here it is 50 years later or more. A lot of folks still remember the old deadly vaccines, and so they think vaccines are bad, I'm not getting one, and they just don't understand we've come a long ways. Here is the modern vaccine we're most often exposed to. That's recombinant DNA, where the antigen is used, but only part of the antigen. We're going to steal a section of the chromosome that codes for the production of a surface marker. Then we're going to insert that little piece into the chromosome of something harmless, such as yeast. And now we have a ptarmigan cell, which has mostly yeast, but a small piece of DNA that codes for the production of the antigen surface marker. Because the harmless cell has a little bit of the DNA of the antigen, it's going to start making a surface marker, which is kind of strange. So now suddenly the yeast has its own surface marker and a surface marker of something deadly, like HIV. At this point, we inject the recombinant DNA, a ptarmigan, and our body's going to attack it, destroy it, even though it's harmless. Our body doesn't know. Our body just knows that it's a foreign antigen. And this then causes T and B cells to be made, antibodies, so that when we encounter the real thing, because this is kind of fake, right? Like let's say it's a fake HIV, really. Then when we encounter the real HIV, we have memory T cells, we have B cell antibodies, and we are on the spot ready to destroy it. Monoclonal antibodies are based on what our body does. Our body makes antibodies, but here we can make them in a laboratory and make them monospecific, meaning they are able to recognize and attach to only one type of cell, one type of receptor. And this makes sense if you think about having something injected in your body. Let's say you have breast cancer, and you want that to attach to just the breast cancer tumors. You don't want them having all sorts of other functions causing problems in your body. So they're all clones of one unique parent cell, ready to do one job only. Here's an example. We use in medical treatment something called immunotherapy. And these are commercially prepared antibodies. They're going to bind to specific cells, and we use it for detecting pregnancy, cancer, and some diseases. But they also can increase our body's defense against cancer by manipulating our own natural immunity. So, just like before, they're going to stimulate APCs. APCs are going to stimulate the T cells and B cells. We get antibodies. It's a big cascade effect, all brought about by the monoclonal antibody. First example. Some of the most aggressive breast cancer tumors have an overactive HER2 receptor. Now, most breast cancers don't fit this. Okay, I think about 26% have this aggressive feature. But when it's there, it's scary. And we have a treatment in the form of monoclonal antibodies that are going to bind to the surface of these tumor receptors and flag the tumor for destruction. If you remember, the antibodies are going to alert and stimulate macrophages and other APCs to flood the area and destroy. Look at that marvelous photograph of macrophages. Second example is the use of immunotoxins. We combine a toxin with a monoclonal antibody, and we can insert that into someone's body, and it can block basic functions. So, say in the case of HIV, it doesn't directly kill it, it just makes its life difficult, and so eventually you might kill that target cell. Another example is the interferon that releases cytokine. And if you recall, cytokine is a chemical released by our own body, our own white blood cells, that stimulate the entire immune system. It revs it up. So we can just do it ourselves, inject a interferon cytokine. It's going to slow down the viral replication, may not kill it, but just kind of makes its life difficult. And it, as I say, stimulates macrophage and other APC activity. We use it for hepatitis C, which is a serious one, HIV, and many other diseases. In summary, we have two kinds of immunization that are passive. That's the loaned antibodies, where we get them across the placenta or from breast milk. There is the active form, which we make our own B cells and T cells because we're exposed. We can be exposed to the MHC marker, which I mentioned. This is what people are so afraid of, and it's kind of ridiculous because this isn't done much. Or the recombinant DNA, which is so amazing. We are going to steal a section of DNA from the antigen. We're going to transfer that to a harmless cell. So we have a tarmogen. We're going to inject that, and now our body is alerted to, let's say, HIV. So if we're exposed, we are rapid and focused, and hopefully we destroy the real thing. Monoclonal antibodies are the commercial use of antibodies that usually we make on our own, but we can specialize monospecific antibodies and use them in patients that have, say, breast cancer, the HER2, which is super aggressive. We can bind to the receptors. We can combine a monoclonal antibody with a toxin, which may block the function and slowly, hopefully, kill something like HIV or cancer. And finally, interferon, which releases cytokine. Cytokine is something our own body can make, but why not give us some help with some injected cytokine? And that's going to increase macrophage activity and also slow down the multiplication of hepatitis C and HIV. So hey, are you going to get that flu shot this year? I hope so.